So we left off last time talking about the mass moment of inertia, the parallel axes theorem, and I wanted to look at a quick example here that does that. If I wanted to find the mass moment of inertia about this axis AA, so I could use the parallel axes theorem and transfer the moment of inertia about this axis OO to this axis AA. So saying that the moment of inertia about that axis AA that's at the edge of this thing would be the moment of inertia through the mass center. That term has to be through the mass center plus the mass times the distance squared. And you could then look up in a table value or something the mass moment of inertia through the center. That's a fairly well-known value, 1/2 mr squared. So I plug that in there. Then the mass of this thing is, of course, m, and the distance that we are shifting at this perpendicular distance, this parallel distance, is, I guess these axes are parallel, and when I said perpendicular, we're looking at right angles on both of those. Then we've got we're shifting at the radius, so we'd have the distance squared would be r squared. Totaling that up, we have 3/2 mr squared about that axis AA. And, you know, I wanted to look at this problem as we began, just to recap the parallel axes theorem, that this term has to be through the mass center. And also, when you look these up, if you go back to some additions. Well, in the past, there's been some errors in the cover flaps of certain editions of the textbook in terms of the mass moment of inertia, and it was predominantly with this one here for a cylinder, this 1/2 mr squared. I think there's certain editions that have mr squared, and then there may have been some problems with this circular disc that had the same value. So if you've got a textbook, you may want to double check those. To that end, I also produced this handout, and I put it up on the website. If you're coming here from a different direction, I will put the location of that website in the description of this video, but I've got this handout there in PDF form. I blew it up a little bit here, make it a little bit easier to see, but I always think that it's a bad thing to have errors in the cover flap of textbooks, because we usually tend to think of that information as fairly solid. Also, if you're looking at doing exams and whatnot, if this kind of information is necessary on an exam, I will provide a copy of, like I said, this handout on the exam. I'm not going to necessarily tell you which one you need to use here, and you may not even have the axes that you want. You may have to use the parallel axes theorem to transfer it to an axis that you want, but this information will be available to you. So I just wanted to take a moment and note that. So go ahead and check those cover flaps in your textbook. Make sure that these are correct values, or you could just use this handout if you wanted to, or both. So parallel axes theorem. Maybe we'd want to spend some time and prove to ourselves that that's correct. You know, maybe we get a good argument going. Is it 1/2 mr squared? Is it mr squared? You know, my cover flap says this. Your cover flap says that. What is it? So let's spend some time seeing if we can derive this. So I'll take this thin disc, and actually in the cover flaps it's the cylinder, but we get the same answer. And instead of saying the ZZ axis, I'm going to say the O axis, and I'm going to divide this up. I'm going to take a piece that looks like this, where this distance here is dr, and the distance radiating out from the center is r, and then the amount of sector there, the angle there, is d theta. And we're going to say that the major dimension here is r, the radius of that thing, and of course the thickness, and we'll of course take that thickness as constant. Well, we saw last time that the mass moment of inertia was the integral of r squared dm. So if we talk a little more about dm, that could be rho times dv, as long as we have a constant density, which we'll take constant density in this. So if we expand that a little bit, I need to talk about dv. So I could say it's rho times r d theta, that's essentially that distance across there, right? R d theta times dr, that's that distance there. So that finds the area of that rectangle, if you will. And then the thickness, that's into the page, so that will then give us the volume. So if I put those into the equation, I could say that I about the axis OO is equal to the integral from, let's see, we're going to be integrating for theta, right? Well, I'm going to have a couple integrals, aren't I? So maybe I'll just, I'll leave it like this for a little while. So, okay. So I'll say I've got the integral, and I'm going to say that I have r squared, and then I'm going to substitute in my dm, which is rho times r times d theta dr t. Okay. So I'm going to divide that up a little more carefully. I'm going to say certainly that we'll take the rho as a constant. We're going to take the thickness as a constant, so I can pull that out. So I can say I about OO is equal to, I'll have the density, I'll have the thickness, and then I'm going to break this into two integrals. I'm going to have the integral from 0 to 2 pi, as this theta goes clear around this thing. And d theta. Have you talked about double integrals in math somewhere? Okay, great. So, and then I'm going to have, so I've kind of taken care of this d theta. Now I have this dr that I have to deal with. So I'm going to have a dr. That's going to be the integral of r, and it's going to go from what? 0 to the extreme outside edge would be capital R, 0 to capital R. And if I group up the r terms, I have r squared and I have r, so that is what? R cubed. Anything else? I've taken care of the r squared, the r, the d theta, the dr, the rho, and the t. So we should be good. And you could do these in any order. If you chose to put the theta inside the r, that would be fine. Sometimes one order or another makes it a little easier. I don't know that it would be a big deal in this one. So if we go through this, I could say that this is equal to rho times the thickness times the integral from 0 to 2 pi of what are we going to have? R to the 4th divided by 4 d theta. Okay, which when you go through the integral there, you're going to have rho times the thickness times r to the 4th divided by 4 times 0 to 2 pi. That would give us 2 pi, wouldn't it? Let me tidy this up a little bit if we want to. We could say rho times pi times t times r to the 4th divided by 2. And you might say, oh, I thought we were trying to debate, was it 1/2 mr squared, or was it just mr squared? You know, that's the mistake in the cover flap of the book. And here we got a whole nother mess. But we don't have the mass term, do we? So it looks like we need to factor a mass term out of there. So mass that we'll say is m. Let's set that up as rho times the volume v. So the volume for this whole thing is going to be equal to what? Pi r squared. That would be the area of the circular area. And then if I multiply it by the thickness, wouldn't that be the volume? So pi r squared times the thickness. That's the volume times the density rho. So I want to try and factor that out. And doing that, I could say then that I about OO is equal to, let's see, there's one right there, there's one right there, there's that. And of course, we could say that this r to the 4th would be r squared times r squared, wouldn't it? So I could say then that we have 1/2 times the mass. That takes care of everything else except for the r squared. So that'd be our answer there. Questions with that? So most of the time, probably your employer is not going to want you to go through this fun calculus exercise. You're probably going to look up in the back of a book or something and find it for some standard shapes. And we'll talk about problems where we can combine these shapes and deal with things that may not be in the back of the book and put them together in ways that we can make new shapes. But for something basic like this, pretty straightforward, good application of integration. You may have seen this problem in a math class, not that you probably used math's moment of inertia there very much, but it gave you an opportunity and exercise in integration. Questions of that? Okay. So before we go on to that, looking at different pieces and whatnot, I guess I better get a backing sheet in here. So I want to talk about one last thing, radius of gyration. And there'll be two takes on this, two types of people in here. One person says, I want an equation, I don't want to think about this. Okay, so for them, the radius of gyration, k, is equal to the square root of the mass moment of inertia, I, divided by m. And we could, of course, rearrange that and say that I is equal to k squared times m. If I look at a unit standpoint, we know that the units on I are distance squared times mass. So this works pretty well for that. Do the units here work? Yeah, if you have, let's say, kilograms times meters squared, and then you divide by meters squared, and is that going to work? Let's see, I is, let's see, kilograms meters squared, m, oh, that squared shouldn't be there, should it? I just have m in the denominator. Are we okay now? I is going to be in mass units, kilograms times distance squared. Mass will be just in kilograms. Oh, I really messed that up. There we go. Okay. That's what everyone was saying, right? Okay, thank you. So then I have this underneath the radical. I get to cancel this with that, and we come up with the square root of meters squared, which would be meters. So this is a distance. Okay, and like I said, there's some of you that you just want the equation. Okay, if someone gives me k, what are they telling me? Well, if they give you k and they give you the mass, you really are able to calculate I, right? And then there's people, what does this mean? Okay, and this what it means sometimes bothers people. But let's say that we had a body here, and we had some reference axes. And we talked about the mass moment of inertia about this axis. So OO, and we talked about I, OO for this particular body. Come up with a number, right? Well, what the radius of gyration says is if I have this axis here, where can I concentrate all of the mass in this infinitesimally thin unit of mass? So this goes on to positive infinity and negative infinity, and its thickness is 0, and this distance here is k. Okay? So what the radius of gyration does is it sets these two systems equal to each other. So when they talk about radius of gyration, if you really want to think about that is, what that is a distance where you could place all of that mass in this infinitesimally thin region and have the same mass moment of inertia. Okay. Things that are infinitely thin and go on from negative infinity to positive infinity kind of bug people, so most of the time you're pretty good just remembering that equation there. If someone gives you the mass and the radius of gyration, really they're trying to tell you what I is. Questions with that? So radius of gyration, and indeed it is a distance, has units of distance. Well, let's try a problem. We've got one more problem that I want to tackle, talking about I, and then we will start certainly next time talking, because this problem will take a little while, but we'll start next time talking about what can we do with I. Why do we don't measure and calculate I just for the sake of doing that. We will use that. So that's where we will go next time we get together. But let's see if we can tackle this. Someone has given us this control wheel. Flywheel, if you want. You can think of it like a wagon wheel. It has 8 spokes. It has this heavy center hub, and then it has this heavy ring around it. They used to make flywheels like this with spokes and whatnot. If we get a little bit of time, we'll talk about how we can tell where that flywheel is made, whether it's made in Europe or whether it's made in America. But so we got those 8 spokes. And if I cut through this thing, so slice through that where one of those spokes is, or 2 of those spokes are, I've got a section that looks like this, and we've got all of those dimensions are in millimeters. The one thing that's a little different is the cross-section of the spoke is circular, which probably makes sense, hopefully, and it has a cross-sectional area of 200 millimeters squared. Everything else that you don't see units on are in millimeters. And we're told this thing's made out of steel where its density in the metric system is 7830 kilograms per cubic meter. So we'd like to take the, come up with the mass moment of inertia about this center line, about this axis that's going through this hub. If we were to put that hub on a shaft, what would its mass moment of inertia about that be? And one of the things that I probably need to use is I need to figure out the I for a ring. So if I look at this and this, and it's got some distance here, where we could say that this has some Ri and it has some Ro. Ri is the inside radius, Ro is the outside radius. Ri is hopefully smaller than Ro because you don't want the hole on the outside. And then we could, if we wanted to, we could talk about the thickness of this thing or the depth of this thing, depending on whether we're talking about something thin or thick. And using our work, we could say that I about the center line, that's through this axis here, I about the center line would be equal to 1/2 MO times RO squared. That's just for the whole thing, right? And then what we can do is we can subtract the center. So I'm going to subtract then 1/2 MI times RI squared. So I take the whole outside and I subtract the center. This used to be kind of perplexing to students, but you've spent now a while dealing with like SolidWorks or Inventor, where you actually draw things like that, right? You'll draw the large sphere and then you'll cut away the inside sphere. So I think students are probably more comfortable with that now than they ever have been. Well, if I make my substitutions for my mass, I could say that MO, that's going to be equal to pi times RO squared times the thickness times the density. And I could say likewise for MI, that's going to be equal to pi times RI squared times the thickness times the density rho. And when I do all of that, when I substitute these into there, I can come up with the expression that I about the center line is going to be equal to pi times rho times the thickness divided by 2 times RO to the fourth minus RI to the fourth. And if you didn't want to do this substitution, I mean, I'm just probably going to the back of the book and looking up those values and making that substitution. If you didn't want to do that, we could have looked at this guy here that we'd finished up with. What do we have? Pi times rho times the thickness times R to the fourth over 2. We could have taken this for the outside and subtracted the inside, right? Okay. So hopefully nothing new there. Make sure I've got that right. R to the fourth. Okay. Well, probably that's worth maybe pausing at least and looking at this thing. R to the fourth, that's a powerful concept. We're taking it to the fourth power. So as the radius changes slightly, that's going to make a tremendous difference in the mass moment of inertia, isn't it? So let's say that we had this problem and we were fixed for time here. We have a real mess on our hands. We only have a couple minutes to finish this on a test. Maybe it's a multiple choice test, so if I could just narrow it down and guess a little bit, maybe I could save this thing. And we're going to have to probably find the mass moment of inertia for this center hub. So this will be the hub. And then we've got the spoke, right? Now how many spokes do we have? 8. So that's times 8. Yeah. And then we have the rim, don't we? Okay. Now we unfortunately find out we only have time to do one of those. So which one would probably be the most important to do? The rim. Yeah. I could take just a few minutes, find it for the rim, and then I'm going to select the answer, if it's a multiple choice test, as the number a little greater than that, right? Because the spokes in the hub are not going to add a lot to that. So let's go through. Let's see if we can validate that kind of thinking. So if I want to talk about I for the rim, what's that going to be? I could say that that was pi over 2 times, I need the density. What density do we have? There's our density, 7830. And because we're in the metric system, maybe I won't put the units down, but we definitely have to be careful. This is meters, and what do I have in the rest of it? Millimeters. So I think I'm going to work these dimensions. I'm going to convert all of these millimeters to meters. So as I go through that, I've got pi over 2 times the density times the thickness. What's the thickness for the rim? 75 millimeters, right? So that's 0.075. And then I need to multiply by the inside radius. What's the inside radius for that thing? Or I'm sorry, not the inside, but the outside radius. Now it looks like outside to outside I'm up 400, right? So that would be 400, half of that is 200, so I'll say that's 0.2 taken to the 4th power. And then I'm going to have to subtract, now I get to subtract the inside. So what's the inside of it? 300, so 150, so 0.15 taken to the 4th power. So run through those numbers, let me see what I get. So I get 1.0089, and that would be kilogram meters squared. And that's just for the rim. I've got probably too many significant figures there, but I think it's going to be important because really, frankly, the final answer is not going to be a whole bunch different than that. So, you know, if we were really pinched for time on a test, and there was one of the answers that was, you know, maybe 1.01 or 1.02 or something, that'd be a good option, right? Okay, we know it's not going to be less than this. Well, let's do the hub. I for the hub. What's that? Well, pi over 2. Again, 7830. And now our hub has this width. This is not dimensioned very well. I flunked drafting class. So, drafting is good, but I never really liked it. When I went on interviews, I always asked them where their drafting department was, and if they couldn't produce a drafting department, I always figured that'd be me. So let's see, where are we? 0.12? Well, that sounds kind of silly, but I mean, as you start looking for a job, you can really tailor your career into what you want by your first job, right? If you don't like sitting at a desk, you probably don't want to get a job where they got a little chain hooked to your desk, right? Okay. You have to be realistic about this. I mean, if it was all good, they call it a hobby, right? You don't get paid for hobbies. But you can certainly, you know, kind of craft your career by your job selection. Okay, so we've got that. Now we need what? The outside, which is going to be 100 divided by 2, 0.05, minus the inside, which is 50, so 0.025. So what does that turn out to be? Anyone get 0.0086? Yeah. Kilograms per meter squared. We got the same units. So our methodology that didn't amount to much holds true. That's a fairly massive piece. I mean, that's where we're probably going to mill a keyway and things like that. But it's just so close to the center, it doesn't make much difference, right? Okay. So let's see if we can do the spokes then. So see if we can keep this here. I'll do the spokes here and then right up on the page. So I for the spoke is going to be equal to, well, as the spoke goes, we've got, in general, the spoke has a circular cross-section, right? And we have I about this axis. We can get that pretty easily out of the back of the book. I think that is 1/12 ml squared, where L is the length of the spoke if we were to go and look at this in the back of the book. Yeah, thank you, 1/12 ml squared. But I don't want it about that axis, do I? I want it about this centroidal axis for the whole piece. This is the center line for the entire thing. So I'm going to have to shift this thing. I'm going to have to shift this down. So I could say that I for one spoke about here was equal to 1/12 ml squared plus the mass times this distance d, if you will, squared. Classic parallel axis theorem, right? Okay. So let's look at that in our problem. So we could say that we have 1/12 ml squared plus, what's the length on this thing? I mean, that's 100, isn't it? If I take 50 and 50, L would be equal to 100. And what's our distance d on this? How far are we shifting this from the center line? Yeah, d is actually equal to 100. Okay, so this is a little bit confusing in that, in our case, this L is equal to 100, and d is also equal to 100. But that should work out pretty nice, because if I then say that I have 1/12 ml squared plus md squared, where d is equal to L, I could really say that this is equal to 13/12 ml squared, right? Just going through the math on that. So let's see. The mass. I could say that this was 13/12. Mass is going to be equal to the density times the volume. Mass is equal to the density times the volume, which would be equal to the density times the area, the circular area, times the length, right? So rho times the circular area times the length. So I've got 13/12, the mass, which is rho, times the area of the circular cross section, times the length, that's the mass, times the length squared. So I could say that this was 13/12 rho times the area of the circular cross section times the length to the third power, right? And the reason I'm kind of having to make a big deal about this is because we were given the circular cross section, weren't we? So if I put this all together, then we have I for the spoke is equal to 13/12 times rho, that's 7830, times the area of the circular cross-section is 200 millimeters squared. So what's that? That's going to be actually 0.0002 meters squared. Okay, I have to divide by 1,000 twice, right? Okay, so 0.0002. So that's the area. And then I have the length of this thing. What's the length of that? The length and d are both 100. So what's 100 in meters? 0.1. Okay. Did the units work out on this? This is going to be kilograms per cubic meter. This is going to be meters squared. This is going to be meters cubed. So in the numerator I have meters to the fifth. The denominator I have meters cubed. So I should end up with what? Kilograms meters squared. So that works good. Let's see what I get then. I get 0.0017. That's good. Yeah. Okay. And that's for one spoke, right? Spoke singular. So what I want to do, I want to multiply this by 8. And what do we get? Because we got 8 spokes. So 0.0016. So still not very much. So I could say then that I about the center line would be equal to I for the rim plus I for the hub plus I for all the spokes. Yes? Yeah, I didn't do the math doesn't look quite right there, does it? Yeah. .0136. Anyone else get that? 0.0136. We good there? No one? Yeah, okay, great. Okay, good. Okay. Yeah, that didn't make sense. That was some new kind of math, wasn't it? Okay. So I for the rim, I for the hub, and then I for the spokes. So we'll take it that we've already multiplied it by 8. So for the rim, what did we have? 1.0089 plus I for the hub, 0.0086 plus for all of the spokes, I'll use that number there, 0.0136, which nets us 1.031 kilograms meters squared. So again, if we would have just taken it for the rim, added a little bit to it, probably would have been okay. Questions with that? So I mean, what if someone gives you a flywheel that looks like this? It's maybe round like this. There's the center, and then this section is kind of carved out, so the cross section of this would look something not like that. So the cross section of this looks something like that. What would you do? I mean, I don't want to have to try and integrate this thing, so what would we do? We just find it for this, and what approximation would we make? It's going to be a little less, isn't it? It'll be a little less. Good. Questions with us? Well, when we get together next time, we're going to take this and put it together. Remember when we were dealing with the kinetics of a point, we got to use that force is equal to mass times acceleration. We said with a rigid body, we're going to have to concern ourselves with the moment is equal to I times alpha. And this equation probably is not that simple, because whether I'm rotating about the mass center or some other point actually affects the problem. So we're going to have to delve into this a little more, and then we will work some problems. So that's where we'll go next time. Take care till then.